Hi, hello everyone. Welcome back to Deep Learning Video Lecture Series. This is Dr. Chiranjeevi Manike, Professor in Data Science and Cybersecurity, MLR Institute of Technology, Hyderabad. So in this lecture, I'm going to cover Perceptron algorithm, and then we'll see a numerical example, that is how we train the Perceptron to learn AND gate function. So first step, that is we need to initialize the weight and bias values, and also we need to supply the learning rate eta. So and these steps need to be repeated till all the data points are classified correctly. Data points means, like, suppose if you take any data set and there will be rows, like if you take a classification as an example, classification, like suppose there are some 100 samples, so there will be input features like x1, x2, x2, x3 and so on, and if there are n number of features, and there will be one output also. So for each instance, that means for each record, we have to correct, we have to check whether this is classifying correctly or not, all this. So that is the meaning. Repeat all the data points until all the data points are classified correctly. So then in this part, what we are going to do here is, so here we are going to choose a data point, so x with the target value y, and then we'll compute the target. Okay, so and based on this is not a fixed one, this is just an example, that is to classify the binary. It gives only the binary output, that is either 0 or 1. If the value, like if this is a nonlinear activation function, so that value is greater than or equal to 0, then it has to produce output 1, otherwise it has to produce the 0. But this function and the outputs would vary from one problem to another problem. So next, once we compute this y hat, that is then we have to check whether it is the matching with the actual output or not. This is a predicted one. This is a predicted output. It has to match with the actual output. So if it is not matching, that means if y is not equal to y hat, then we have to update mainly the two, that is weight and bias. Weight and bias. So bias need to be updated. So if you look at the generalized equations, so equations of this weight and bias, how the update, so you can just like wi, so wi is a new 8, so wi equal to wi plus delta wi, and similarly the bias also, bias plus delta b. And what is this delta? Okay, so what is the delta? That is what changes need to be, what adjustment need to be done. So in this case, so delta wi, that is equal to, so learning rate times y true value minus y predicted value times xi. Okay, this is eta, learning rate, and y true, that is actual values, yp, that is predicted value, times xi, that is corresponding input. And similarly delta b, that is bias, what amount of change need to be done. So learning rate times y true, that is y actual value, y predicted value. So this is the way, and these equations we are going to use to update this weight and bias. So let us take one simple example here, and before we see a numerical example, and let us try to understand what do you mean by this learning rate. So I'm not going to give in detail explanation about this learning rate. I just want you, because it is very beginning lectures, so I just want to give a brief idea about what is a learning rate, how it is going to affect the learning process. So the learning rate determines how fast or slow a model learns. For example, the small learning rate where n is 0 or n tends to 0, close to 0. So the model learns slowly, So which requires more iterations to converge. More number of iterations are required to converge. And it reduces the risk of overshooting, but may get stuck in the local minimum. But if the learning rate is large learning rate, so that means the eta tends to 1 or more, then the model learns quickly, very quickly, but it might overshoot the optimal solutions. So it may fail to converge and lead to instability in learning. So how we select the optimal learning rate? So optimal learning rate, that means which balances between the speed and the stability. It allows the model to reach an optimal solution efficiently. So let us go to the example, that is Perceptron example. In this case, how we are going to see how to train a Perceptron to learn a AND gate function. So for this we need to take one data, that is, and this is, I think, yeah, so this is visible. So this is AND gate truth table. There is nothing different here. AND gate truth table. So now what steps need to be followed, like as we discussed in the algorithm, Perceptron algorithm. The first step, Perceptron model, that is need to be understood. So what is the nonlinear activation function? Like suppose G equal to, so W1 X1 plus W2 X2 plus bias. So then if G, so that means activation function f of G equal to, so 1 0. So that is if G greater than 1, greater than 0, or else if G less than or equal to 0. I think yeah, so if G is greater than 0, that because AND gate output, okay, so AND gate output, the G is greater than 0, then it has to produce 1, and if it is less than or equal to 0, then it has to produce 0, because the nonlinear activation function is the sum of like bias plus sigma I is equal to, that is weighted sum, I is equal to 1 to n wi xi. Okay, so this is the way we are going to calculate. So this sum, the total should be greater than 0. So greater than 0 means this is AND gate truth table. The 1, that means the output 1 corresponding inputs are x1 x2 are always, both the inputs are 1. So the remaining all cases it has to produce the 0. So to match that, so we have to define this nonlinear activation function in such a way. So that is the way, that's why. So we have we define like this. So G is greater than or equal greater than 0. If it is less than or equal to 0, then it has to produce the output 0. So you can also check it whether it is working, whether it is right or wrong, or whether it is accurately predicting it or not. So first let us try to understand how this Perceptron learns this AND gate function. Next we have to initialize some parameters. What are the parameters need to be initialized? So that is weights need to be initialized. So suppose W1, and here we are going to take W2 and also 0. So both W1 and W2 are initialized to 0, and bias is also initialized to 0, and eta initialized to 1, learning rate. Okay, so this is the initialization part. So weights are assigned, initialized to 0, bias is initialized to 0, and the learning rate eta is initialized to 1. Next, the third step is the training using the Perceptron learning rule. So that what we discussed, like how do we update the weights and bias. So that concept we are going to apply here. So this is very simple to understand. It's not even a difficult thing. But in the coming lectures, we'll be going to discuss more real world examples, so that there will be many complex mathematics would be there. So So this is only for understanding this, how the learning, the basic understanding. So let us apply this. So we have initialized the weight and bias, and then the second step, the first step and second step, then and the third step. The first step is the model equation, that is nonlinear activation function, and the second step, initialization of the bias and the weight parameters, and the third step, the training using the perceptron learning rule. So now let us take this first instance. So first instance, the input x1 and x2 are 0, output is 0. So now then we have to substitute these values. So g equal to w1 x1 plus w2 x2 plus b. Okay, so we have to plug all the values, like we have considered the first instance. So now if you plug the values, and I would also write for a easy recalling purpose w0 and w1 w2 w1 equal to w2 equal to, both are same. So and 0, and bias is equal to 0, and learning rate eta equal to 1. So then if I substitute this x1 and x2 of this first instance, then the z would be, so 0 times 0 plus 0 times 0 plus bias 0, then it is equal to 0. So as per the nonlinear activation function f of g, that is 1 0 if g is greater than 0, and if g is less than or equal to 0. Okay, so then we have to check it. So f of 0, and for this f of 0, g equal to 0, so then f of 0 equal to, so it is less than or equal to, so then it is, output is 0. So now, and this is a y hat. Okay, this is a predicted value. So now the next step is we have to check this actual output of this sample is 0, and the predicted output is 0. So then both are matching, so there is no need of updating any parameter here. Okay, let us take second example. So then g equal to so 0 times 1, 0 times 0 plus 0 times 1 plus 0, so that is equal to 0. So then f of g, that equal to, that is f of 0. So 0 means it is less than or equal to 0, it has to produce output 0, so that is correct. So this is correctly predicted, and there is no update required. And let us take another sample. So in this case g equal to, so g equal to, so 0 times 1 plus 0 times 0, 1 times 0, yes, 0 times 1 plus 0 times 0 plus 0, that is equal to 0. So for this case also f of g, that is equal to f of 0 equal to 0, this is also correctly predicted. And the last instance, if you take, and the g is equal to, this is w1 x1 plus w2 x2 plus bias. So w1 x1, that is 1 times 1 plus 1 times 1, 0, these are all zeros. So 0 times 1 plus 0 times 1 plus bias is equal to 0, so then it becomes 0, but f of 0 equal to 0, but actual output is 1, so that means it's not equal. This is y hat, so it is not equal to, so that means it's wrong. So then update need to be done. So how do we have to update the weight and the bias? Okay, so let us update the weight, that is w weight we are going to update. Both w1 and w2 need to be updated. So W1 means previous weight, that is 0, plus learning rate is 1 times y predicted, and for this instance we need to consider here. So because this perceptron predicted wrong, the predicted output is wrong, it is not matching with the actual output, so that's why. So here we have to consider this instance. So 0, that is previous weight, Wi plus this delta Wi. So this delta Wi is equal to learning rate times y actual value, y predicted value times x1. Okay, so then we can plug all the values in this case. So learning rate is 1 and y2 is 1 and the predicted value 0 times x1 is 1. So this is equal to 0 times 1, that is 0 plus 1, that is 1. Next, similarly, W2 equal to W1 plus learning rate 1 and the y predicted value, y2 value 1, predicted value 0 times x2, that is 1. So this is again equal to 1. And then bias B, previous 0 plus y. So y true, that is 1, y predicted is 0. That should be multiplied with the learning rate. So now this is equal to 1. So then we have to we have updated, and then let us check for this instance with all updated values whether it would be able to classify correctly or not. So G, I am going to recalculate for this instance. So G equal to W1 again W2 x2 plus bias is 1. So now it is equal to 1 plus 1 plus 1, 3, which is greater than 0. So the output, okay, so the y hat equal to 1. So it is correctly predicted. And let us check for the remaining instances also. Like suppose the second or the first instance. So first instance, that is x1 x2 0 0. So now in this case, so W1 0 x1 0, so W2 x2 0 plus 1. So now 0 in this 0 0 1. So 1 is greater than 0, it is wrong. So y, the output is, it is wrong. So then again these values need to be updated. So if you update these values, then let us check how these values are going to change. So for this instance, the output should be 0, but it has produced this sample classified as 1, output as 1. So now let us check. I'm going to remove this part. So W1 B1, W1 W2 and also the B1. So learning rate is same 1 and y true value 0 here. Y2 is 0 and the predicted value is 1. So similarly in this case also, so true value 0, predicted value is 1. and similarly here for bias also. So 0, 1. Now, so 1 plus, so here 1 minus, so, yeah, so this will becomes 1 minus 1 that is equal to 0. So similarly 1 minus 1 that is equal to 0, and here the 1 minus 1 is also equal to 0. So then if it becomes 0, so then there is no, because the previous updated value, so previous weight and the bias values are remains the same. So I think it will enter into this kind of a loop, and if there is no such a, so what could be done here? So let us recheck it once. So let us check it. So W1 equal to 0, W2 equal to 0, and bias equal to 0, and the learning rate equal to 1. So that is, then we substitute the values in Z, that is W1 x1, so 0 times 0 plus 0 times 0 plus 0, that is equal to 0. So if 0 that is less than or equal to 0, so it has to produce the output 0. So f of 0 that is correctly predicted, and second instance, so 0 times 0 plus 0 times, so 1 times 0, 1 times 0 plus 0 that equal to 0, and here also 0 it is correctly predicted, and similarly, and this is a case we need to check. And for the third instance, 1 times 0 plus 0 times 0 plus 0 that is equal to 0, it is correct. And if it is like suppose 1 times 0 plus 0 times 1 plus 0 times 1 plus 0, it is produced 0, so it is wrong prediction. So then weights need to be updated. So Wi is equal to Wi plus delta Wi. So in this case Wi is 0, that is W1 0, and this is learning rate, so I can directly substitute the values here. Learning rate is 1, and the y predicted value, so y actual value is 1, y predicted value is 0, and times x1 is 1 here. So this is, let me write this part here. So 0 plus 1, that is 1, so W1 becomes 1, and similarly W2 also becomes 1, and then bias equal to B plus delta B, that is equal to learning rate times y true value. Y true value is 1, y predicted value is 0, times x2, that is 1. Sorry, there is no x1 here, so that is learning rate times the y true value minus y predicted value. So 1 times 1, that is equal to 1. So this is the way this learning, this training, the Perceptron training will happens. So then once it is done, that means all the samples are classified correctly, then, and that would be used to test the model. So then we will deploy that model in the real world. Thank you for watching this video.